In this lecture, we are going to look at wave propagation in the atmosphere. When you have no atmosphere, the waves go in straight lines like this. When we have atmosphere, the rays bends towards the densest medium. The air is densest, closest to the ground, so typically you have the rays bend towards the ground. As for visible light, also the radio waves can be treated as ray optics on a large scale. You see here, for instance, you have wavelengths which is comparable with this obstacle here, then you get waves on the other side. However, when the waves are very narrow or short compared to this obstacle, then you also have rays at this side. So it depends on the wavelength. So as long as the wavelength is very short, corresponding to the characteristic dimension of the object, you get ray optics. And we have some fundamental laws of ray optics. And here you see an incident ray and a reflected ray. These two angles are equal. And then you have Schnell's law, where you have this bending given by the formula here, coming in here, going out here. And this medium is thicker than this one. I see that because this angle is smaller than that one. And this n, or the index of refraction, is given by the speed of light in vacuum divided by the speed of light in the media. So n is always more than 1. And as I said before, the rays bends towards the denser medium, as shown here. We have height here, and we have a stratified atmosphere, and it bends down like this. Then, since the index of refraction of air is very close to 1 in vacuum, we usually use what we call radio refractivity instead of n, and that big N is n minus 1, 10 to the 6th. And we have an empirical formula for that. That's 77.6 divided by the temperature measured in Kelvin, multiplied by the pressure in millibars plus 4,810, multiplied by the water vapor pressure in hectopascal or millibar, divided by the temperature also in Kelvin. And here you see a calculation of water vapor pressure. Here you have the temperature, and here you have the saturated water vapor pressure in hectopascal. And since both the pressure, the water vapor pressure, and the temperature also all varies with height, also this radio refractivity will also vary with height. For a normal, standard, well-mixed atmosphere, the D and DH, or the variation in radio refractivity with height, is minus 40 N units per kilometer. So here you see we have dense air, we have less dense air. Typically, dN, dH drops with 40 per kilometer, and it bends towards the densest medium. Here you see something called the K factor. There is a relation between this and the K factor, and that will come on the next page, I think. Yeah, here we got it. We are using what we call K value. It includes ray curvature and the Earth radius. The definition of K is 1 divided by 1 minus A, which is the radius of the Earth, divided by 1 divided by R, which is the curvature of the wave. And that is given by minus 1 divided by small n dndh cosine alpha, and since we are shooting close to the horizontal, this one is equal to 1 because this angle is roughly 0, and then we can approximately set this equal to dndh because that was quite close to 1, and then you get this formula, and then you put in dndh with a big N instead, and you have this. And if you put in the radius of the Earth and a normal dndh of -40, then you see that you have a K value of 1.33. And here you see different K values. This is 2/3, 4/3, which is 1.33, which is the normal K value. Here is infinite, and here is a negative K value. And here you see the ray bending relatively to the Earth for different K values. And you see that for infinite, the wave bends with the same radius as the Earth. If it has a negative value, it bends more than the radius of the Earth. If it's less than infinite, it bends less than the Earth. And if it's 2/3, it bends upwards. So, and then if K equals 1, that means the same as if there was no atmosphere, so then it shoots in a straight line. Here are some examples. You have less dense air here, and you have dense air here up here, and then you see that the ray is bending upwards. So in order to reach the other antenna, you have to shoot downwards, and then that looks like the Earth has come closer. Okay. And then in this example, dndh was 78. That means a K value of 0.66. And then we have what we call a sub-refraction. And if we have dndh equals to 0, that means that equal distributed density, the same as no density, and then we shoot in straight lines. If we have dndh less than -157 N units per kilometer, exactly -157 gives K equal to infinity. And if it's less, then K is negative. You have to shoot upwards in order to reach the other antenna. And you also have the possibility of never reaching the outer antenna, and then you will have what we call a radio duct. And here is what they call a ground-based duct. You have an antenna here. You are shooting in this direction. It bends downwards, and then you will have a shadow area here. So if you have an antenna here, you will not reach it. Here is also another way of showing a ground-based duct. Here you have the antenna here, and here you see you have an inversion layer, and here you have bending in this direction, and due to this inversion layer, you will have bending in this direction. And if you have the other antenna here, you will have more than one ray coming from one transmitter to the receiver. And then you will have what they call a ground-based duct, and you will have a signal that will vary in time. Yeah. And that is what happens, multiple propagation. When we have more than one ray reaching the receiver. And multiple transmission is in fact for long parts the main cause of fading. And it only happens when dndh varies with height. That is that we have different regions here in, for instance, a ground-based duct. you have a region here, another region here. And then you have a receiver here, a transmitter here. In this region, you have a straight ray going from the transceiver to the receiver, or the transmitter to the receiver. And then you have a ray reflected down here. And then you have more than one wave reaching the receiver. And a wave or the length this goes is longer than this goes. So then you will have different phases of these two waves, and you will have a signal that varies with time if this one here varies with time. Here is an example. We made some measurements in Norway, in the middle of Norway. We measured on a 13 gigahertz part, which was quite long, 43 kilometer, and it was shooting over sea. And in fact, we observed multipulse activity during daytime. Usually over land, the multipart fading activity is during the night, but over sea we saw it also during the day. And here you see the signal level as a function of time. Here is the lowest level measured in the time frame. Here is the upper one. So the larger the difference here, the more activity. And you see here we have a lot of activity in these two, around these two times here. And we also have arrows, which is shown here by those arrows going here. And also here we have arrows. We also were so lucky that we have the radio sound at one of, in the middle of, between those two sites. And here you see a duct. Typically here is minus 40 N per kilometer. That is the light blue one, and the dark blue one shows this duct phenomena at about 400 meters. So in this case, we have more than one ray coming to the antenna. And if we look at the weather at that time, we see that we have a variation in temperature, a large variation in temperature during this period. And that large variation in temperature gave us this duct. Elevated ducts, then you have normal propagation here, and then you have a thicker area here. When the energy that comes from your transmitter goes into this elevated duct, it's transported along this elevated duct. And since the radio energy is not released from that duct, it can travel very long, much longer than under normal conditions. And how does a duct come to life? Well, during the day, the sun will warm the ground, and the air will start to do convection. Warm air, the ground heats up the air, and warm air goes up and cold air comes down, and you created a well-mixed atmosphere during the daytime. In the night, for instance, here you have a cold night, the moon is up, you see some stars, etc. The ground will cool this region, and you will have temperature inversion. That means that the temperature here is larger than down here, and then you have a ground-based duct. In the morning, the sun will start to heat the ground, and this ground-based duct, which has grown through the night, will be eaten from the ground, and then you will have an elevated duct. So no fading during daytime. It starts during night, and it's reversed in the morning hour, typically 1 hour after the sun has risen. Here you see a map of ducting probability, and it shows the percentage of time where the DNHDS is less than minus 100 N units per kilometer in May. You also have some charts from other periods, but this is for May. And here you see that the probability of having large DNDH values is close to the equator. So the closer you are to the equator, the more likely it will be that you have ducts. And that is, of course, because of the high temperature and also the moisture in the atmosphere. If you go, for instance, to Norway, where I live, you see it's just 1%, not 75 here as in western part of Africa, but it's still fading, have multi-part fades on long parts, typically during the summertime. Yeah, and here is the ducting probability that we will use in the calculations given by the CZR. So, and we will use them later. Here is just showing you this. Yeah, and I think this is where we will end now. We will look in an appendix on the wave bending once more.